Okay, so I gave you guys a note. If you can't hear me or if anything happens, everything that I'm about to say is already in the note. Plus, I'll make a note from this lesson and I'll add it to those notes. So you'll have both notes that you can compare. So when you play with the app, there's a lot of features. If you look in the top left-hand corner, if you look over here, you'll see that you have an option between manual, oscillate, and pulse. You'll see that I always use the oscillate function, because if you use oscillate, you're going to get the perfect sinusoidal waves. If you use manual, you have to create the waves yourself. And if you use pulse, it makes these funny triangular waves, which we don't like. Cool. And then I always set it to no end. And no end means that it's not going to hit something and bounce back. So I'm not going to get what's called interference, which is a topic that we do later. Cool. So I set that to no end. And then to start with, I always set the tension high. And the reason is because if you set the tension low, the string is very, very, very loose. And at very high frequencies, the waves basically look like tiny little lines. I'll show you what that looks like just now. Cool. And then I set the damping to none, very important. I set damping to none. And what that does is it keeps the waves constant. It means that it doesn't lose energy and becomes smaller over time. Cool. So oscillate, I set over here. I set it to no end over there. I set damping to none. And I set tension to high. Tension we can play with. And in fact, I'm going to give you a project to do where I want you to change the tension. But for now, we're going to keep the tension high. And then basically the only two things I play with are amplitude and frequency. Those are my only two variables, if I can call it that. So just keep that in mind. Okay, so it's set to oscillate, it's set to no end. I'll just show you quickly what the other ones do. If you're on manual, you literally have to make the waves yourself. So I'm moving this up and down. So I can go down, and go up, and go down, and go up. But if I don't time it perfectly, I'm not going to get, oh, there's nice waves. So not too bad. And if you do pulse, pulse will give you these funny waves like this. And if you put an end in, you're going to get the reflection. So you're going to get that, which we don't want because we want to see the waves individually. So we're going to put it on oscillate. That's quite good. Okay, so the best thing to do is pause, restart. And then what you can do is you'll see here, I'll quickly point it out. Over here, there's a sort of play pause button over here. So it's play pause. Good morning, Tandy. Play pause. And what you'll see with that is that if I tap on that slowly, I can create the wave slowly, 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 slowly. So I'm tapping on that play pause button. If you can see it's lighting up. And all that does is it lets you create waves as slow as possible. But you can just do that if you want to. Go to no end. There we go. So the play pause button, or you can go into slow motion and you can have a look at it like that. So you have all those options. You have slow motion, you have normal, and you can do the play pause to literally go frame by frame. And you'll see why that's useful later in terms of measurements. Cool, and I'll show you quickly what the tension looks like if you make it lower and if you increase the frequency. You get these ugly sort of waves that look like that. Not very useful to analyze. So much nicer when you have lots more tension. Cool, any questions so far?
No,
everyone
sir.
good? Yep. So it's quite a fun app, but the trick to playing with the app is just to keep things fixed. In other words, what I say in the note that I've already sent on the Google Classroom is don't change too many things at once. Keep a couple of things fixed and play around with one or two variables. And the two variables that we're going to play with today are amplitude and frequency. So we're going to keep everything else fixed. Cool. And then the other thing you can do is you can add a ruler, and you can add a vertical ruler and horizontal ruler. You can't change the angle, meaning you can't do diagonals and stuff. Okay, so while we're here, let's have a look. So we can measure the wavelength of this wave if we take a measurement over here, and if we take a measurement over there. Would you agree with me that that's 2.4? So I can measure that 2.4. And if I really wanted to, I could measure it again at the end over here. And that total distance there would be 4.8. And it makes sense that if one wave is 2.4, two waves is 4.8. Oh, but you know that we can measure the wave from anywhere. So we could also put the ruler over here. And we could do the same measurement again. So we can check over here and check, measure that, measure over here. And you'll see that I get the same 2.4 if I measure it from, let's call it the time axis to the time axis. And then you can keep measuring from any point you want. So you could even choose a point like that, not a very nice one, but you could, and you could say measure it from that point and then count the full wave, look up, down until it gets to the same point, measure it to there, and you'll get your same 2.4. Cool. Would you agree with me that I'm cheating, that it's not exactly 2.4?
Well, sir,
I'm not really cheating, but would you agree? Yeah, talk to me. What is it about the ruler that doesn't allow me to measure better?
It's just centimeter.
Correct. And it's actually
millimeter.
correct. It's not a millimeter scale. And also it's actually measuring to every second centimeter. So if you look at the scale, it's actually 2 centimeter scale. So I have to estimate the middle one. So the uncertainty in my measurement is plus or minus 1, meaning that this measurement is probably plus or minus 1 centimeter. So it's pretty accurate. It's not great, but it gets me there. And you'll see later when we do calculations, the uncertainty doesn't affect the result too much. We get more or less the same answer depending, irrespective of which way we, irrespective of how close we measure. Okay, so in the notes now, what we do is we play around with things and we say, okay, let's keep everything the same and change one thing. And the one thing that we're going to change is the frequency. So we're going to change the frequency and see how it affects the wavelength. So keep damping the same, keep tension the same, keep amplitude the same, no end, and oscillate all of that the same. And all you're going to notice is that 2.56 at the frequency is going to come down. Let's take it to about 1.21. It doesn't really matter. Ooh, then play a bit. And pause. Then we can put the ruler somewhere. Let's measure from point to point over there. And let's go to that. Then we can measure, take that one. Oh, that's approximately there. And that's probably about 5.1 centimeters. The wavelength. Cool. And then you'll see later we use this little Half-Life symbol. I don't know if you played the game Half-Life.
No.
So if you've ever played the game Half-Life, you'll see that it has this symbol that looks like this. It's the Greek letter lambda. Also, it's the Greek letter lambda, and that's the symbol that we're going to use for wavelength. So this here is for wavelength. Ooh, it's all in the notes, don't stress. And we can measure the length, 5.1. Okay, so let's do a quick recap. Did I increase or decrease the frequency?
You increased it.
Oh, careful, sorry, no, other way around. So
Oh,
I
you
was,
decreased.
yeah, I was at about 2 point something, and I took it down to 1.21. So I decreased the
Okay,
frequency.
you decreased it.
Correct. And then what did you see happen to the wavelength?
Increased.
Increased, correct. And then you could do a proportional increase, decrease. So we could start with a fixed number. You could start with something like, let's choose a nice number like 2.5, let it play. Cool. And then take a measurement. Let's have a look. Top of the thing. Take that measurement there. Remember that it's not that accurate, so we have to be careful. We'll just estimate. So let's estimate approximately 2.5. When the frequency is 250. Oh, that's wow. That's a nice coincidence. that's purely coincidence. Okay, and then we can save that. Then we can exactly half the frequency, so we can take it to 1.25. So we go down to 1.25. Let it play. Have a look. Ooh, and then once you find a nice place to measure it, take it there, and screenshot, and then we can look here, and that's approximately there, and that's approximately 5 centimeters. Cool. So would you agree with me that when I halved the frequency, I doubled the wavelength? I'll show you now quickly. I'll show you the photos.
So are you using the same speed?
I'm using the same speed, correct. We haven't changed the speed of the wave. So you'll see later we can calculate the speed of the wave based on both of those calculations, and we'll get exactly the same number. So if you look at the original one here, I started with the 2.5 at the bottom in the frequency. And then I measured a 2.5 centimeter wavelength. And when I halved the frequency, I doubled the wavelength. But yes, the speed of the wave hasn't changed. Cool. Any questions so far? No, we're good. So Gloria, excellent question. That was very important. We haven't changed the speed of the wave. You'll see later that by changing the tension, we can change the speed. So when we do the calculations, we can base it off of these two calculations, and you'll see that we get the same speed for the wave. Cool. Then what you can do is you can measure the period. The period is a little bit more difficult because period requires a timer. So you've got to put the timer in front of the wave. Now I played around with this a lot, and it requires you to be a bit, you've got to be systematic. So you've got to constantly press restart. You've got to press the restart on this one over here. So you've got to restart both of them, and you've got to make sure that you're on pause in order to do this. So you've got to pause the wave, you've got to restart it, and you've got to restart the timer. So you've got to do all those things simultaneously. So I'll show you what happens if I don't start the timer. Would you agree with me that that time is sort of meaningless to me because I don't know where I started the wave and where I stopped the wave? So what I'm going to do is I'm going to restart the wave. I'm going to restart the timer. And then what I'm going to do is I'm going to start the wave on play pause mode. So first start the, first start the timer. And you'll see that because the wave is paused, the timer is paused. And now if I do this, can you see that the wave and the timer move simultaneously? So have a look at that. Now what I want to do is I want to get that green dot back to the equilibrium line. So I want it to end over there. And can you see by doing that, I can measure the period of the wave, which is 0.8 seconds. So we can call this here the period. And this we give capital letter T, and we can say the period of the wave is 0.8 seconds. In other words, it took exactly 0.8 seconds for one wave to form. So it's the time for one wave to form. Everyone happy with that?
Yes, sir.
Whoopsie, get rid of that. We don't want that. So let's see what happens if we carry on. If we carry on, we can create another wave. There's another half a wave. 1.2 seconds makes sense because it took us another 0.4 seconds to make half a wave. And if we keep going on, let that green dot hit the line again, 1.6, and that's the time taken to create two waves. So 2 waves equals 1.6 seconds. Therefore, 1 wave equals 0.8 seconds. And we give this value t. T is equal to 0.8 seconds, the period for the wave. Also, it's a little bit tricky to play with because it's not easy to determine. So it's not that straightforward as far as calculating it goes. But you've just got to play with the functions. You've got to press the pause button and you've got to make sure that you constantly reset your things. Cool, so then I can change the frequency. Let's exactly double it. So let's go to 2.5. Let's go exactly to 2.5. Start the timer. So you can see it went from play to stop, which means the timer started. And then I can start play pausing and oscillating. Now I want to get the green one back. And there we go. And we can say that the period is equal to 0.4 seconds. Cool. And then we can go to photos and have a look. So we started here with 0.8 seconds when the frequency is 1.25. Then we doubled the frequency, and what happened to the period? The period doubled. Oh, careful, the other way around. So half, correct. So have a look here. The frequency is whoopsie, I don't want to do that. I want to write on you. Let's write on you. There you go. So there it's 1.25 and 0.8. And if we go to the next one, it goes from 2.5 to 0.4. Cool. So I started with a frequency of 1.25 and a period of 0.8. And when I doubled the frequency, I halved the period. Cool. Everyone happy with that?
Yes.
Yeah. So you'll see why this makes sense, because period and frequency are inversely related. So you'll see that there's an inverse relationship between the period and the frequency. Go back to that. Okay, so before we continue, are there any questions? Would you like to say anything? Is there anything you would like me to test? Is there anything you'd like me to do on my side in terms of the app, and something you would like to test or think about? Anybody? No? You good? Is there anything that you can suggest that we should try out, or are you happy? Are you good with that? If you're good with that, okay, then we can continue. So what we'll do is we'll do amplitude, then we'll take a break, and then we'll come back and we'll look at how we can use frequency, period, and wavelength to calculate speed. But let's first look at the amplitude. Okay, so reset. I'm going to get rid of the timer because I don't need timer for amplitude, and I'm going to get my rulers back here. I'm going to take the horizontal one, and I'm going to just shove it down to the bottom here because I'm not interested in that just yet. Cool. So let's set the amplitude to something small so we can have big space to double it, and then keep the frequency at 2.5. And there we go. Cool. Then we can take the ruler. So you can take the ruler and you can measure the amplitude at any point. So I can measure it there, and you can see it's 0.5 centimeters. Hang on. Oh, 0.5, sorry. We want it at the halfway line. Yeah, more or less there. Cool. So if we measured that there, it's approximately 0.5 centimeters. But I could also measure it at the top here. And I could say that over there. It was confusing me because of the scale. I realized the scale is half units, double units, so that's 0.5 centimeters. And would you agree with me that the amplitude is the same all throughout? So I can measure the amplitude top and bottom. You good?
Yes.
Good, good, good. Okay, now what we can do is we can measure the wavelength, and we can see what effect does changing the amplitude have on the wavelength, if any. So are there any predictions from what you know from IGCSE? If I change the amplitude, will I affect the wavelength if I keep all else things constant?
The wavelength decrease.
Cool, so you say decrease.
So what was the formula again?
The formula is speed is equal to wavelength times frequency. So the question is, if I change the amplitude, will it affect the wavelength?
Yes.
If you want to make the peaks higher, you have to make the waves shorter in between.
Okay, so that's a good hypothesis. That's interesting. So let's think about that. Let's keep yours as an idea. Does anyone else have any ideas that we want to think about? Yes, no, maybe. I mean, in terms of your hypothesis as far as the question goes.
If we keep that, if we increase the amplitude,
Sure.
doesn't that mean the frequency was increased?
It's possible. So let's see if that happens. So what I'm going to do is I'm going to measure the wavelength now as it stands. So I'll measure it before. Then all I'm going to change is the amplitude, meaning I'm not going to change the frequency, because the frequency I'm going to keep constant. So I'm not going to change that. Okay, so here's the first measurement. Oopsie, don't do that. Do that. Nicely on the line. There we go. And get you nicely on the line. And that's approximately wavelength is equal to 2.5 centimeters. And then we're going to remember that the amplitude is 0.5. So amplitude is equal to 0.5. Let's just call it centimeters because it's a measurement of length. Ooh, and then the frequency stays constant. So we're going to keep this constant. Keep constant. Done, save. Okay, so all we're going to do is increase the amplitude and we're going to double it exactly. So we're going to take it to 1 centimeter on the dot, 1 centimeter exactly. Ooh, press play, let the wave oscillate a little bit, press pause, and then we measure the wavelength again. So then we measure here, and we measure here, and we get 2.5 centimeters when the amplitude equals 1 centimeter. Frequency was constant. Cool. So then we go back to that, and we have a look. When the, oh, why is that so dark? Okay, there we go. When the amplitude is 0.5, the wavelength is 2.5. When the amplitude is 1, the wavelength is 2.5.
So it stays the same.
It stays constant, correct. And the sort of hint is that we didn't change the frequency. And remember that we'll see later that there's a relationship between the frequency and the wavelength. So at a constant frequency, the wavelength is constant. Increasing the amplitude has no effect on the wavelength. You're just making higher waves. You're just oscillating to a greater point. So you're just moving further away from the origin. But you'll see later, amplitude has meaning. Amplitude has meaning in other contexts, and that's either today's second lesson or tomorrow's first lesson. We'll talk about how the amplitude is useful. Cool. Any questions about the app? No? Good? Cool. Because what I'm going to do is I'm going to set you a project based on the app, meaning I'm going to give you a scenario and I'm going to ask you to do something. It's quite straightforward. Basically, what I'm going to do is I'm going to ask you to change the tension. So if you change the tension, you can obviously see that you change the frequency, the wavelength, if the frequency stays constant. And then all you're going to basically do is you're going to use the wave equation later to calculate the speed of the wave at different tensions. And then you can tell me a little story about how does tension affect speed, for example. At high speeds, you get, at high tension, you get watt speed, and at low tension, you get watt speed. So that's going to be a little project to do later. Cool, guys, take a 5-minute break. I'm going to pause and stop the lesson, and then come back. We're going to start the lesson at 8:40, meaning log on approximately at about 37:38, so we can get started at 8:40. Cool.
All right.
Good. See you in a bit.